The chip everyone is fighting over. A $30,000 to $40,000 chip, waiting lists, export bans, spends most of its working life doing nothing. Not broken, not idle by choice, starved, waiting for its own memory to hand it the next byte. Here's the decade in two numbers. Measured the same way, the math inside these chips got roughly 100 times faster in 10 years. The pipe that feeds them data got barely 10 times wider. Every year, the fastest processors on Earth spend more of their time doing the one thing they were never built for: waiting. Last episode was about why memory got expensive. AI is trading 3 gigabytes of yours for every one of its own. This one is about the stranger question underneath. Why is memory the thing AI fights over at all? Because here's what actually ran out. It wasn't arithmetic. Chips multiply numbers absurdly fast, absurdly cheap. What ran out is the ability to deliver numbers to the math fast enough to matter. Engineers call it the memory wall. By the end of this video, you'll know exactly why a machine that can do 2 quadrillion operations a second sits around like a bored chef, and why the entire industry is rebuilding itself around the delivery problem, not the cooking. Picture the chip as a kitchen. The math units are the chef, the memory is the pantry, and every ingredient has to walk through one door. For 10 years, we upgraded the chef relentlessly. 2016's flagship AI chip did about 21 trillion calculations a second. Today's does over 2 quadrillion, measured the same way, roughly 100 times more. The pantry door? In 2016, it passed under 1 terabyte a second. Today, about 8, 11 times wider. 100 versus 11, that's the scissors. And it isn't one bad generation, it's the trend. Peak compute has grown about 3 times every 2 years. Memory bandwidth about 1.6 times. 2 curves compounding apart for 2 decades. Compute up 60,000-fold, memory bandwidth up about 100. To be fair, memory occasionally fights back. The newest generation stacked faster memory and narrowed the gap slightly. The chef-to-pantry ratio actually dipped. But zoom out, and even when memory catches up for a generation, the decade gap doesn't close. Think about what that ratio means physically. Today's flagship can perform nearly 300 calculations for every byte its memory can deliver. The chef can chop 300 times while one ingredient walks through the door. For the chef to stay busy, every byte that arrives must be used 300 times. And AI's biggest workload uses each byte about once. That collision is the next block. When a chatbot writes you an answer, it generates 1 token at a time, a word, a chunk of a word. And to produce each token, the model must consult everything it knows. Not part of it, all of it. Every weight, the billions of numbers that make up the model, is reread from memory for every single token. To say one word, the model reskims its entire library. Then it says the next word and reskims the library again. Now run the kitchen math. Reading a byte, doing roughly 1 calculation with it, moving on, that's 1 operation per byte delivered. The hardware needs hundreds of operations per byte just to stay busy. Decode delivers about 1 versus hundreds. Serve 1 user at a time, and the compute units are busy less than 1/5 of 1% of the time. So of course, Nobody serves one user at a time. Providers batch. Hundreds of conversations share one pass through the library. That's the great trick of modern inference, and it works. But measured studies still find the chip's math units busy maybe 20 to 40% of the time in decode, and across production inference broadly, 5 to 15% is typical, which is why the cold open isn't a metaphor. Most of that chip's working life is waiting. And batching has a ceiling because every conversation drags luggage. As your chat grows, the model keeps working notes on everything said so far, the KV cache. Longer context, bigger notes. The notes live in the same fast memory as the library. Enough long conversations and the luggage starts evicting seats. The batch shrinks and you're sliding back toward that terrible one-user math. Now the part that makes all of this feel less like an engineering oversight and more like physics. Back in 2014, chip designer Mark Horowitz published the numbers everyone in the field still quotes. Adding 2 numbers on a chip, about 1 picojoule, 1 trillionth of a joule. Fetching those same numbers from memory, hundreds of times more energy, closer to 1,000. Read that again. The math is not the expensive part. The trip is. On a chip, it is literally cheaper to add 2 numbers and to bring them to the adder. That's the memory wall, not a design mistake. Physics. Wires cost more than arithmetic, and distance costs more than both. Once you see the wall, the industry's strangest moves start reading like one plan. Shorten the trip. Move 1. Stack the library on top of the reader. That's HBM, memory piled into towers, drilled through with vertical wiring, parked millimeters from the processor. Last episode, we saw what that costs. About 3 gigabytes of your RAM sacrificed per gigabyte of theirs. Now you know why they pay it. They are not buying capacity, they are buying proximity. Move 2. Keep the hottest ingredients in the kitchen itself. Chip designers now carve out ever more on-chip memory, the small, fast kind that lives next to the math, so the most used bytes never take the long trip at all. Move 3. When one chip's memory isn't enough, wire dozens of chips so tightly they behave like one. Their memories pooled into a single giant library, with data flying between them on dedicated links instead of ordinary networks. Each of those moves is its own machine, its own physics, its own episode. Today, you just need the shape. Everything is about the distance between the number and the math. So run the ledger one last time. The arithmetic in an AI answer costs almost nothing. The math became nearly free while nobody was watching. The billions in chips, the memory shortage that ate your RAM, the towers, the pools, the pipes, all of it is the price of delivery. You are never paying for math, you are paying for the distance between the memory and the multiplier. Not compute, delivery. And the delivery problem doesn't stop at the chip's edge. The moment data has to leave one chip for another, it hits an even harder wall. At today's speeds, an electrical signal in a copper wire falls apart after about 1 meter. It can't even cross its own rack. Next, Why AI is abandoning copper for light, and what dies at 1 meter. That's the next layer down. Subscribe and it'll find you.